Good afternoon. It's a pleasure. It's really nice to see so many people here to hear from Susan Greenfield, whom I'll be interviewing in a moment. So I'd like to thank you for coming. Before I do that, I'd like to acknowledge the Bedigal people, who are the traditional custodians of the land on which this meeting takes place, and pay my respects to elders, past and present. So we're very privileged today to host Baroness Susan Greenfield, who will present her talk on a novel approach to Alzheimer's disease. So Baroness Greenfield is the founder and CEO of NeuroBio Limited. She's a neuroscientist, and she told me before that she was a classical scholar, and before she moved into psychology and then into neuroscience. She's also a writer and broadcaster. She's published lots of papers, and she's based mainly at Oxford University, but has held research fellowships in various parts of the world, in Paris, in New York, and in Melbourne. She holds 32 honorary degrees, this must be a record, okay, from the UK and foreign universities, has received numerous honours, including the Légion d'honneur from the French government, and honorary fellowships from the Royal College of Physicians and the American Academy of Achievement Golden Plate Award, and the Australian Medical Research Society Medal. She's a fellow at the Royal Society of Edinburgh. So Susan will talk to us for about 40 minutes, and then we'll have a Q&A. It says a live Q&A. I hope it's lively. And I thank you all for coming. So Baroness Susan Greenfield, over to you.
Thank you. Oh, thank you, Henry. It's a huge pleasure to be here. One of the great honours that Henry omitted was that in 2006 I was Honorary Australian of the Year in the UK because I apparently showed Australian values. And it doesn't get me past customs any easier or passport control, but it does testify, without sounding too cheesy, I do love coming back to Australia, and I come back a lot, and I love the excuse for coming back, and indeed the chance to share with you what will be a heretical talk. So can I assume that most of you, everyone here is biomedical, or is there any sort of general? So forgive me then if I'm using, well, don't forgive me, because I will be using technical and neuroscience terms, but just like to double check. Okay, so we'll start with the journey of the company, actually, because it's quite unusual when you are a tutor at Oxford University, as I was, to suddenly jump ship and set up your own company. But let me introduce you, and we can talk about that in the lunch break, if you like, of the challenges of what it's like when you're an academic suddenly to go into the private sector. But here we are. There's some of the team. You can see down here. When you have your own company, you can choose your own wallpaper. So I chose as faux forest, so it's not really a forest, obviously, but you can see we have a large team comprising of 3 senior and 5 junior scientists, and also when you have a company, you're one-for-one pretty much with management, and that always surprised me why one would spend a lot of money on people who weren't scientists, but that's another story. Over my years at university, which you'll hear about, we developed what we think is a compelling story for Alzheimer's that is nonetheless hugely still controversial. We believe we have a unique insight into the process of degeneration that also actually lends itself to non-core assets that relate to oncology, skin health, and aging. Our goal is to, nothing humble here, revolutionize the treatment of Alzheimer's and challenge dogma. I think it's very exciting challenging dogma. And again, it's not for the faint-hearted. And again, those of you who might be faced with that in your own careers, I'll happily discuss that with you over the lunch. So why is it then? Let's start with the issue of why has it taken so long to develop an effective treatment for Alzheimer's? Some might argue we're still waiting. I think there's been too much focus on the anti-amyloid drugs. That's the first heresy, and I'll try and explain why and defend that. Sorry if I'm offending you already. Second, there is a pre-symptomatic time window of up to 20 years, so you're closing the door after the horse has bolted if, when you present after some 20 years of degeneration for a treatment, because it's only then you have the cognitive impairment. And third, there's the assumption that all brain cells have the same generic profile. And those of you who are neuroscientists will know one size doesn't fit all. Neurons are not all the same. So let's just unpack those very briefly. The too much focus on amyloid with the various anti-amyloid drugs that have come out. This is a paper that I was just referring to Henry, who said, what is the, when you say there's an absence of amyloid, absence of what amyloid, I can't answer that question, but that is the reference. And this is a review, an interview I gave back in 22 on the amyloid obsession. And whilst I think it does, of course, play a role in the picture of Alzheimer's, it's not the primary agent driving it. How can it be if it's not there in the early stage pathology? How can it ever be the primary target? And most recently, lecanemab, which has gained permission by the regulatory authorities in the UK, MHRA, which might think to be, that's a good sign. On the other hand, NICE, who are our regulatory body for approval of purchasing on the National Health Service, said it's not sufficiently effective. I actually got on my phone the front page of the local tabloid when I was in the lounge at Heathrow, which actually says, despair that these anti-amyloid drugs are not being approved for NHS purchase because they're not sufficiently beneficial. So again, we can argue long and hard about amyloid if you wish later, but these are my reasons. It's primarily the fact that in early stages, the primarily vulnerable cells don't show any signs of amyloid pathology. Second is the time lag that I'm sure you're all familiar with, of some 10 to 20 years. Now, not only does that provide an impediment to developing a proper treatment if the cell's been degenerating for 20 years, but also it does beg an explanation. Why is that the case? And any theory of Alzheimer's will have to come up, to my mind, with an explanation of why brain cells degenerate for 10 to 20 years and only then do you see cognitive impairment. It is a problem. This is from our Alzheimer's Society and Alzheimer's Research UK, probably the same here in Australia, where it's very urgent to try and get people to get an early diagnosis, and many people won't because they say, what's the point if there's no cure? On the other hand, as in the case with lecanemab, the Alzheimer's Society was saying, not only is it a problem that it's not approved for the NHS, but we don't know who would give it to anyway because no one's volunteering to be tested. So it is an issue that we have to address. Thirdly, and I'd like to focus on this mainly, is why is not all neuronal populations are the same, as you can see from not all brain cells, one size doesn't fit all. They have different properties, and we know that neurodegeneration is a highly selective process, and it's only apparent early on in certain cell groups. This has been ignored, and this has been known for a long time. Since 1981 it was first mooted. And if we knew what was special about these vulnerable cells, surely we would have an insight into the mechanisms driving neurodegeneration. So how are these vulnerable cells different? Well, basically, we've got 4 clues. And this is a summary, all of the literature, not of our work at all. The first is this really prescient review by Martin Rosser. By the way, you can have this talk if you want it. So if you'd like to. So don't worry about taking photos. Not the order. But you're very welcome to have this with the wonders of modern technology. You can have it. It's not like the old days of slides. So you're very welcome to have this if you wish. And then this excellent review by Theophilus much later on, really presenting a very strong case for these cell groups being the primary ones, primarily vulnerable in neurodegenerative diseases. And he termed the phrase isodendritic core. I think because isos being equal, these cell groups are characterized by very extensive dendritic fields, and actually we know, and something else I used to work on, that agents are released locally from the dendrites. They all intermingle. They have something called volume transmission, which means that they communicate in a very non-specific, non-classical way that nonetheless ensures that they are functioning for as long and as well as possible, as befits cell groups that underlie arousal and sleep-wake cycles, which they do. So that's the first. These are the primarily vulnerable cells. And what's really exciting, and this is really a reason for sitting and reading the literature, and this happened when I was in the 90s when I was still an academic, and this was a light bulb moment from Nancy Wolfe, who showed that at 4 weeks gestation, the brain is divided already into 2 plates, the basal and the alar plate. And what's exciting is that acetylcholinesterase, acetylcholinesterase is present even though there's no cholestyl-transferase in these cell groups, and they have retained plasticity. And moreover, fourth thing, when you apply acetylcholinesterase to these cell groups, you can see it has a trophic action. So let me just repeat these 4 clues. One is the isodendritic core are the primarily vulnerable cells for degeneration. 2, they have a different embryological origin. Nancy Wolfe calls them global neurons because they're like fountains with the amines, but it's the same thing. 3, they all, irrespective of their transmitter, contain acetylcholinesterase. What the hell is it doing there, this huge glycoprotein being released? And one of the actions of it, independent of hydrolysis of acetylcholine, is to promote cell growth, as shown here. So let's put those things together. That's an interesting thing. What could be the salient part of the molecule that's doing this? Well, acetylcholinesterase is present, it turns out, in neural and non-neural cells without its normal substrate. It can be released in a calcium-dependent, potassium-evoked way. You can block its site irreversibly with nerve gas, as it happens. We collaborated with Portman Down, so we know it's nothing to do with its enzymatic activity. It promotes cell growth, as we've just seen, and it does so through calcium influx. So what is the salient part of the molecule? If we knew that, given these are primarily vulnerable cells, perhaps that will play a part not only in normal development, but also in Alzheimer's. So what can we have as a clue? Well, acetylcholinesterase normally exists as a so-called tetramer. That's 4 catalytic subunits joined by disulfide bonds, G4. What's interesting, in the developing brain, however, the G4 form isn't the dominant form, but a monomer, unimaginatively entitled G1, is the dominant form. Now, why is that interesting? Well, in Alzheimer's disease, you get a revisiting of that profile where you have a recapitulation of the developmental situation where that ratio changes. Instead of the dominance of the G4 tetramer, you now have more dominance of the G1. Why should that be? Well, first of all, it shows you that cholinesterase has something to do with Alzheimer's, which is quite interesting, and also that normal development somehow might be linked to Alzheimer's. So what happens is if you are severing those disulfide bonds, so you only have the monomer, it can't oligomerize, then what happens is you could have these C-terminal peptides liberated. So it means that whenever you see G1, it hasn't oligomerized because the disulfide bonds have been broken and you have a liberation of C-terminal peptides. Now, what we are arguing is the G1 is simply a footprint of the exciting thing, the C-terminal peptides. And here is the hero of the story, the 14-mer T14. This is present in all vulnerable cells, the cholinesterase. You can see it here. And it has a strong sequence homology with amyloid, which is how we found it. Can I also introduce you to T30, which is the larger one that nonetheless encompasses the T14 and allows us use of the C-terminal T15, the 15-mer, as a control peptide. So what you'll see as we go through are use of both T30 or T14 interchangeably. T15 is used as the control. Okay, so that's what we've identified. And we found, when we had this made and we applied it, guess what? It does what cholinesterase does. It promotes growth. And these are a series of papers where we showed its bioactivity. I won't go into them now. If you wish, you can have this talk and check them out. The interesting thing is that it declines with age. So in the developing rat brain, shown here with these westerns, you can see from the embryo through to postnatal, there is a clear decline in the level of T14, and that's quantified here in rat brain slices. That correlates with cell activity measured by voltage-sensitive dye-imaging, which we also have in the lab, and you can see these large cell groups, which we call assemblies, are correlating with the T14, which would figure, if it's letting calcium in, the calcium depolarizes the cell, so that will mean it's more active during development. At George Mason University, we've been collaborating with, and we gave them some of our agents, and they showed here that there was an increase in the surface area of the lamellipodia. By the way, if anyone would like to work with us, we are delighted to share antibodies or T14, T30 with you, because this is a novel idea, and the more people that can actually show external validation, the better, and it might be interesting for you. So afterwards, we can always talk about sharing. We can give you some of our agents if you'd like to try them. Okay, and you can see here that it's blocked by rapamycin, which you might know is a blocker of the mTOR pathway, which is an intracellular pathway implicated both in cancer and in Alzheimer's. So, in the human adult, the T14 correlates human adult brain very well with the mTOR pathway, suggesting this is indeed the intracellular path that follows after activation with T14. And then anecdotally, we've looked at age in the human brain, and you can see this is the midbrain, it declines even in healthy adult aging. What's really interesting is that brain cells share the same ectodermal origin as skin cells. And some of you might be aware there's increasing attention to looking at the epidermis and looking at neurodegeneration. For example, there's a high incidence of Alzheimer's with psoriasis, which is a hyperproliferative disease of keratinocytes in the epidermis. So this notion attracted the attention of Unilever, who you might imagine are interested in skin. And we gave them some of our agents and published in the journal Aging a year or two ago this result, where you can see here, this is in human skin, that is the epidermis, the brown blobs are T14 immunoreactive cells, this was in their hands, and as you can see, there is decline in the epidermis with normal skin aging of T14. And then anecdotally in the lab, and we haven't published this yet, we've looked at sebum using a cotton face mask that we then sort of wrung out and just assayed for it. And amazingly, the T14 obligingly can be measured there. You might wonder why there's no error bar on the plus 45 person, and ditto on the saliva, and that shows the age range of the neurobio team, with me being the one person who is over 45, and they very politely, and that's very generously, can we just 45 plus, and it could have been a lot worse what they did say. But you can see, and this is all just work in progress at the moment, but clearly the T14 could be measured, and there seems to be an age-related profile. Okay, so far then, so what's this to do with Alzheimer's? We've got this great agent that seems to work. It's correlated with aging, it declines with aging. The problem is it can turn toxic, as we showed here. You may be familiar, I'm sure, with exercise toxicity, where increasing levels of methyldespartate, this was one that we happened to do, but others have done the same. As you increase the dose, you go from trophic to toxic, and this is a very well-known phenomenon, because what happens if you overburden the cell with calcium, the excess calcium is taken up into the mitochondria, it compromises oxidative phosphorylation, you get a leakage of electrons, formation of free radicals, and hence cell death. So that's a well-known phenomena. What we showed here was that indeed our T14, if you increased it, could be toxic. So it seems that our trophic toxic axis with T14 can depend on the amount, and we can see Jekyll and Hyde here, where you can see there's the nice neurites shown by the red double-headed arrow, but the cells are in pretty poor shape by the time you get to increasing the dose, or time. So you can incubate for an hour and you get nice neurite outgrowth, but if you keep it on for 24 hours, then it's toxic. But the interesting thing is not the duration or the amount you apply. There's another way of determining whether an agent promoting growth is trophic or toxic. And that wasn't our work. It was Imler and Schramm, and that's age. And they showed that tolerance to calcium changed with age. So from developing cell to mature cell. So that then triggered the idea that neurodegeneration could be an aberrant form of development. So here we see in the rat brain the T14 declining with age, going up in the human midbrain in the Alzheimer postmortem brain compared to age-matched control, so recapitulating development. So that for us was a strong proof of concept. The midbrain, we then looked at the substantia nigra with Greg Cole at UCLA, and at Braak stage 2, even in the nigra, and this is why I'm interested in the co-pathology, even in the nigra, an area traditionally associated with Parkinson's, you can see at Braak stage T, so T14 positive neurons partially filled, fewer cells at Braak stage 5, but much more densely filled, such that if you look at them as a sort of metric, there is an overall increase in this area in Alzheimer's disease, so it shows that. We then look in the animal model of the Alzheimer's. I'm sure you're familiar with the 5-FAD animal model. If you look at the transgene negative animal compared to the actual animal model, you can see the transgene negative adult mouse has virtually no T14, whereas in the 5-FAD mouse, this is Greg Cole's work, you can see clearly T14 immunoreactive plaques characterizing that pathology. So I hope that persuades you that T14 is increased in pathological scenarios, both mouse and human. Moreover, it seems to trigger the traditional markers. So I mentioned about amyloid and indeed tau, and I want to stress, I'm not discounting amyloid, it's just we think it's a downstream agent, triggered indeed by the T14, which is why it's not very effective when you target it with antibodies, because it's a downstream agent, and the real problem is going on upstream. So this is in PC12 cells. You can see that it's triggered amyloid and tau. If you look at ex vivo brain slices, and this is a rather nifty prep that we used, looking at brain slices where you section down the midline and have one side as control, one side as treated, you can see again elevations in amyloid and tau. And then in vivo, and this we're writing up now, when we give the T14 chronically, we're seeing increases again in vivo in amyloid and tau in the brain, and a cell loss, accompanied by a cell loss. And this is being done at the University of Nottingham. So it seems that T14 could be the trigger of these other markers, and that this is the pivotal agent that we should be looking at if we're trying to understand the process of degeneration. So let me take you through now what I think could be the narrative. So we start off with green light. In normal situation, the T14 is present in low levels in these cells, and it's just ticking over. But these cells are different in they have the potential to grow again. If something damages them, and this could be anything, it could be free radical attack due to lack of protective mechanisms, due to lack of scavenging mechanisms as occurs with older age, or it could be a stroke, or it could be anything, it could be an injury, a blow to the head, any damage, it doesn't matter, that kills these cells, unlike the other cells, will retaliate by mobilizing a developmental mechanism because that's their genetic mandate. That is how, from their basal plate origins, they've been allowed to do this. Yeah? So they've retained the ability to grow, which is the T14 mechanism. So they will mobilize that in a misguided attempt to retaliate, to compensate for this damage, which the alar plate cells can't do. But in so doing, because these are mature cells, and we've seen that age is an important factor, now the erstwhile desired T14 for growth is now toxic, so it will kill more cells. And because these cells have a high degree of redundancy, we know in Parkinson's, for example, some say up to 80% of the cells have to die before you get motor symptoms. You have a high degree of redundancy because they're so important, they communicate by volume transmission in a very non-specific generalized way. Because of that, the cells will start to degenerate, and you won't have the cognitive problems. What you might have, and we'll come to this in a minute, is sleep or mood disorders, because that is a feature of these cell groups. And we know that it can be a prelude to Alzheimer's. But you won't have the cognitive problem because these cells will carry on, the degeneration will carry on snowballing. In the attempt to compensate for the loss, they'll release more T14, and the more T14 will cause more damage. So you'll have a feed-forward mechanism instead of a feedback mechanism. And it's not until it spreads to the hippocampus and cortex that now you will have the cognitive impairment, now you will have the appearance of amyloid, and now you will come to the doctor. And now you will have your amyloid antibody. Yeah? So this is our theory for why the amyloid is not effective, why there's a 10 to 20-year time lag, yeah? Why you have a co-pathology, and why you can have sleep disorders as a prelude sometimes. So comfortably thinking we can answer that, let's now, how can we apply this idea? First with the diagnostic. This is Bill Gates. We actually disagree with Bill Gates. We don't, well, because he said before they get too bad, no, before they even appear. Yeah? Henry, oh, you've got some more, don't you? So what we're now looking at are markers. So we wanted to use a biomarker to see if we could detect. And you're very welcome to share in this antibody, and this shows its selectivity. This is a polyclonal. We also have monoclonal being made. We also have another one we're using, a different type of agent, which I'll come to later. And I hope you can see here that it is selective for T14, and that if you incubate it with cholinesterase, then nothing happens. But if you incubate with trypsin, which then cleaves it at those points, then you can see a healthy signal. So we're very comfortable that the antibody will only recognize T14. It won't cross-react with T30 if we apply it. Okay, so can we use it as a diagnostic marker? You're familiar, obviously, with the Brack staging, and the Brack stage 2, that's been classed as asymptomatic. To the best of my knowledge, no one has shown a marker that comes up at the asymptomatic phase, but we showed this in Postmortem Brain, published 2 years ago now. You can see the T14 is indeed mirroring the Brack staging, which again is a reason to think that it might be something really to think about if we're trying to understand Alzheimer's. And in postmortem CSF, you can see there's a clear increase. But we want to look at living CSF. Now, I know that lumbar punctures are not the final choice for looking, final matrix for looking at the diagnosis, but nonetheless, it's intimately connected with the brain. So if there's no change in CSF, then there won't be changes elsewhere. So we've looked initially in CSF with this hospital in Barcelona, who've been very cooperative and helpful, the clinic hospital in Barcelona, who supplied us with living CSF samples. And we showed here a trend, not significant, but a trend with controls then elevated in mild cognitive impairment and then up to Alzheimer's, which encouraged us to look more at T14 in CSF. What we were interested in is not looking at absolute levels, given that there could be variation caused by diet and individual differences. So we then looked at it relative to tau, and as you can see, there was significant correlation of T14 and tau in the control group. What was interesting, really interesting, is that in mild cognitive impairment in Alzheimer's, that had disappeared. And our theory for that is that in the pathological conditions, excessive T14 is being produced, which breaks down the lockstep relationship otherwise present between T14 and tau. And we thought that could be used as a metric. But you could say, well, no, they've already had a diagnosis, so that's not really that helpful or useful. Couldn't we look at the controls and see if we could differentiate them in it? Because if you want a truly symptomatic, pre-symptomatic test, you want to differentiate them. And I think I mentioned previously that another feature of these cells is that early on, they will show aberrations in Alzheimer's. So mood and sleep disorders can be a prelude much earlier on to neurodegeneration. So could we look at mood in the control group and see if we could see any differences with our metric? So these mood disorders are obviously associated with the isoindustrytic core. I'm sure you're familiar with what I used to call the amine fountains that underlie depression and sleep-wake cycles. And if you then look in the control group and divide them, when we looked at the records, there were 10 with mood disorders and 12 without mood disorders. As you can see, the tau was the same in both, but the ratio of T14 to tau was significantly different. And when we then applied a ROC curve to differentiate that as a pre-symptomatic test, it came out as significant at 0.01 with an area under the curve of 0.82, which is significant. So a lot needs to be done on that, but as you might imagine, we're thinking this could be the start of some early stage pre-symptomatic tests that would screen not for Alzheimer's, but for mood disorders, which in turn reflected disorders of the vulnerable cells, which in turn could send you just for a further screen to the doctor. So why is there this correlation? Well, what we think happens is that normally the two are in lockstep, they are co-released. However, in what happens in the mood is more is retained in the brain, so there's less available in the CSF, so you have a mismatch. But then when MCI and Alzheimer's kicks in, we know there is a variant of acetylcholinesterase that is also there, and we think that supplies, and I'll come on to that in a minute, that supplies the additional T14 such you now have the increase. So this is obviously work in progress, we're writing up at the moment, but I thought the whole point of a seminar is to share with you ongoing work rather than just give you a review of what we've done so far. So much of this obviously still needs to be worked on. Nonetheless, we think that you could have a possible rapid screen because it turns out that 50% of nasal secretions are actually derived from the CSF. Now that means, I think you call it a RAT test here, we call it a lateral flow test, is that right? So if I say lateral flow, you'll know what I mean. Please nod on, yeah? Yeah, you are. RAT test sounds so strange to my ears. It sounds as though you're looking at rodents or something. But I'll try and remember it's called a RAT test. So obviously, what would be fantastic would be to have the kind of tests that we're all now socialized to taking, thanks to COVID, yeah? So we know that T14 is detectable in blood and in saliva and in sebum, and this is again in the lab, in nasal secretions. This is a student project where they've got to now do nasal swabs of the team on a day-to-day basis. Imagine how nice that is for them. Because we want to see how consistent it is on a day-to-day basis, is there age and so on. But that is the dream, to then have a lateral flow test. Now, you might say, well, actually, how accurate are these Western blots that you're using? And we're aware that the antibody isn't perhaps as accurate as it should be. And in a sense, for an early stage screen, you only want it to be semi-quantitative. You don't want a specific diagnosis. You want just a go, no-go filter. But nonetheless, we're working with a company called Aptamer. I don't know if you're familiar with aptamers. These are alternatives to antibodies. They're a fifth the size. They can be stored at room temperature. They're not raised in animals, and therefore they have much to recommend them in terms of detection systems. Check them out. And this company, unimaginatively called the Aptamer Group, who make aptamers, are now working with our T14. Well, actually, they're working with T30, which they find better. And you can see here, already in control CSF, they can actually measure it specifically. And in Alzheimer's, it is higher, which is, again, very exciting for us. So what we are now hoping to do is develop this aptamer detection system in a rat test for possible early-stage screening. So this is the excitement of having a company you can actually see something possibly coming out of it. Yeah? So this is our strategy. You'd have a rapid screen. You could buy it in the pharmacy. It'd be cheap and it wouldn't be painful. It'd just be a binary kind of brain health test. If it was go rather than no-go, you'd go to your medic, and under medical supervision, you'd have a saliva test this time, because we're working with the Rosalind Franklin Institute in Harwell, looking at mass spec high precision quantification, or the aptamer, and that would determine if it really was there, and then you'd have all the wraparound of the medical services to develop a care plan, and that's the system that we're using. So these are our strategies, and it strikes me that anyway, if we're thinking about a pre-symptomatic biomarker, it has to be two-stage. If it's pre-symptomatic, you can't all go to the doctors. Well, certainly not with our National Health Service, you can't. So it has to be done at home. And yet at the same time, you can't at home find out you've got a disease as serious as Alzheimer's. So you really do need two steps. Something that just is brain health tells you, no, just go and get checked out, and then one that under medical supervision will determine indeed whether you have got a diagnosis. So if you have, what's the therapy? What are we going to do? So, again, the beauty of the T14 system, if it's true, and I hope I'm convincing you it is that not only is it a direct readout, a biomarker, but it can also be intercepted upstream. And the classic way of intercepting an agent, of course, is receptor blocking. And that's our first prototype drug that we're attempting to do, a nasally delivered preparation that's now officially been recognized by the MHRA. They're our regulatory body. They're the UK FDA. We've been recognized as truly innovative, which is the first step, which is quite good. And the target is the alpha-7 receptor, which is a very powerful calcium ionophore. And that was first shown by its lockstep matching with acetylcholinesterase, you can see here, both looking at the RNA and looking at its binding. Not there in the early days, but exactly when the cholinesterase appears, the alpha-7 appears. So they seem to be very related. And early work that we did was to give bungratoxin, as you can see here. In those days, we called it ACHE peptide, and showed indeed that bungratoxin did nothing on its own, but it did block the T14 effects. So we then wanted to identify it more thoroughly. So with electrophysiology, we blocked NMDA receptors with DAP5 and showed there was calcium, increase in calcium spikes, calcium conductances. But most convincing of all was in oocytes that had been transfected only with alpha-7 receptor, nothing else. So it couldn't work on anything else. Nothing happened with alpha-4 beta-2 or with the butyrylcholinesterase peptide. But what's interesting here, I hope you can see, is that when the peptide was applied alone, nothing happened. It was only in conjunction with the primary ligand, which is either acetylcholine or dietary choline. Then you saw an enhancement. So it was acting as an allosteric modulator. And moreover, the nice thing about the alpha-7 receptor, although it's traditionally a cholinergic receptor, it can also be activated by choline, which can be derived from the diet, and it's therefore not restricted to cholinergic systems, which is why we think this system might even predate the much more selective cholinergic system. If you have an alpha-7 receptor, which is pretty ubiquitous, choline, which you get from the diet, and then the cholinesterase supplying the T14, which seems to be everywhere, you have a very basic, very primitive, widespread system for cell growth that precedes the cholinergic system, I would suggest. And then finally, in the human brain, you can see there's a very high correlation with the alpha-7 receptor in N of 71 and T14 in postmortem brain. So it looks quite strong, the evidence. And moreover, if you manipulate the alpha-7 receptor, either by overexpressing it in cells or mutating it, then the sensitivity to the peptide will change respectively up or down, as shown here. And that's published by Raglani et al. Last year. So what's interesting as well is that if you look in the brain, very obligingly, although cholinergic receptors are plentiful in the brain, in the striatum there's no alpha-7. There's lots of other cholinergic receptors, but for some reason not the alpha-7. And when you look at the application of the peptide just to the striatum, then there is no effect. This is using optical imaging, so you can see everything looks the same. Just check out the histogram. Whereas when we apply it to the nigra locally, then there is an effect. So that, again, seems to argue for site selectivity because of the specificity of having an alpha-7 receptor. Okay, so what's interesting as well is when you apply the peptide, this again is George Mason work, you can see here the clustering not only is an increase in the surface area of the lamella, but the number of alpha-7 receptors has increased. That's actually significant, although it doesn't look it with the small errors. This is our own work from a while ago showing an enhancement of the receptor when we applied 24 hours the peptide. And in rat brain slices, if you slice down the middle again, you can see an enhancement of the receptor. And again, in vivo, when we have done it, not published, compared to the control T15, there's an enhancement of the receptor. So it seems the peptide is creating its own target, which makes things even worse because the more peptide you have, the more alpha-7 you'll have, the more calcium entry you'll have. That's all summarized in this paper that came out this year, where we were amazed that we got away with that title because, as you know, in pharmacology it's very rare and it's a rather extravagant claim to say that an agent's acting exclusively at one receptor. It also means if it's true that any drug that interferes with this would actually perhaps have less off-target effects, which is, of course, the holy grail of pharmacy. So what is this drug? Well, it is the T14 itself merely bent into a circle with the rather unoriginal name of neurobiopeptide 14, which we've now, so here we have the evil T14 binding to an allosteric site. This slide was originally meant for investors, which is why you see these rather clunky images of, of what cyclation means, right? So cyclation is like your hands. So I say to investors, well, cyclating the peptide is a bit like tying your hands behind your back. So, you know, you nudge someone out the way and sit in their chair, but they can't do anything because they've been nudged out the way, and you can't do anything because your hands are tied behind your back. And that is, that's what you learn to talk to investors like that. So anyway, that is the peptide. There it is cyclated. And then this is evidence that indeed it does displace the T14. So this is ex vivo, again using our brain slice prep. In vivo, you can see there at 4 hours when it's been given singly. And then in the post-mortem human brain, this is again is Greg Cole's work where he looked at alpha-lysa, where you look at the metric of the binding of the two with increasing doses of the agent. You can see there's a decrease in the signal. Okay, so does it actually work? We can see how it works, but does it work? And this was done in tissue culture originally, and you can see it reverses the effects both of T3014 and indeed of amyloid, and for cell viability, and it has an IC50 that's 100 times more effective than galantamine, and so 50 times better than galantamine, 100 times more sensitive. And it's effective in mice. This is what we're really interested in. This was done by the CRO Evotec during the height of the COVID time, and we were so excited because against all northern Italy being closed because of COVID, they still did it because they're a medical lab. And so they gave, there's every reason why this shouldn't have worked because we had no idea what we were doing. We didn't know how often to give it, what dose to give, what test to use. It was a real wet finger to the wind. But with their thinking, what they suggested was twice a week for 14 weeks intranasally, looking at novel object recognition. So amazing, you can see the animals put on weight better than the blue controls with given vehicle. As time went on, you can see their weight gain is more impressive, and I think that's a healthy sign for rodents. The test they used was to go with the idea that a rodent will explore a novel object for longer than a familiar object, so that you look at the exploration time of objects. And with that, you can see the wild-type group, the red group was novel. They explored it for much more time, as you might imagine. The saline Alzheimer model animals, the 5-5 models, were living out their genetic destiny. And as you can see, they couldn't differentiate. They couldn't remember what was familiar, what was novel. It was the same. Whereas the animal model group, given our protocol, twice a week, 14 weeks, as you can see, are performing at the level of wild-type animals. And more exciting still for the amyloid lovers among us, was that it really significantly prevented the production of amyloid, as shown here by the gold blobs in the hippocampus. So this got us, as you might imagine, very excited to develop this further, which is why we're now going through the stages, so-called IND, investigational new drug stages of regulation, to bring this for clinical testing to phase 1. This is how we think it compares favorably with the anti-amyloid agents, not least because there will be fewer side effects. Wider applications to this, I mentioned that it was working through the mTOR pathway, and rapamycin, which blocks the mTOR pathway, has been used for a whole range of different things, as you can see here. But the problem, and you can see here that it does block it, our agent also blocks the mTOR. But the problem with rapamycin, it has a lot of side effects, as shown here, because it affects cell viability. Whereas what we have shown is our MBP14, T14 system works selectively on the mTORC1 pathway, not the 2 pathway, which means it doesn't affect cell viability, which means it could arguably be a preferable alternative for the rapamycin indications. So that's one idea. And then we have a pipeline, because obviously we can't just put all our eggs in the MVP basket. I mentioned we were going through IND enabling and phase 1. We've also been talking, it wasn't our idea, but Clinique, some people might know La Prairie. Those of you who can afford skin caviar at the airport will be familiar with La Prairie. They're very interested in aging and also the wider aspects, such as Alzheimer's. There's also a company called Purity Products who've asked us to think about, and we are thinking about, developing a lower level of MBP14, perhaps administered orally, that could be taken like ginkgo or something like that once it's past phase 1. That's another possibility, as well as the intranasal application for Alzheimer's. We're also testing, very obviously, these variants of MBP, and this would be standard. The antibody also could suggest for other treatments. These are the aptamers I mentioned. Small molecules. So all these are ways, because we think we've identified the significant pathway, these are ways in which we now think we could intercept it. Now I'm going to show you the next thing with trepidation. Can I ask, how many molecular biologists are here? So can I ask your patience, please, because I'm about to reveal that I don't know molecular biology, but I would like to present it. But as will become apparent, I probably use the wrong words, and it's not me that's been doing it, but it is very exciting, which is to use antisense oligonucleotides. I'm sure I'm looking nervously at the lady here. Okay, so the reason we're saying this is because we first noticed in the developing animal that the T14 didn't correlate with the normal so-called T form of acetylcholinesterase. As you can see, no correlation. It correlated instead with a variant that is increased in Alzheimer's and in development, the so-called R form of the cholinesterase. And we couldn't explain this because typically that doesn't have the exon from which you can derive T14, as you can see here. So normally it comes from this T form, but this R form, which is expressed in Alzheimer's, and this thing goes up, wasn't there. But we then met with someone called Lorna Harris at Exeter University, who has worked with us, and we're now working with a geneticist, where she's saying, well, perhaps there's these stop codons. You could have oligonucleotides that could actually unzip the T14, and perhaps what happens in nature, in pathology, is this excessive or additional T14 is supplied by alternative splicing with this R form, which we know is raised. So what we're doing now, and this is trying, when I say we, I mean they, of course, doing it, is using these antisense oligonucleotides, and what one of our postdocs is finding is indeed that he's identified 1 or 2 oligos that do switch off the production of the T14 from the RNA, as shown here by the red circle. So that presents itself as another exciting but much earlier stage in terms of research drug that we could use. Yeah. So stage of development, these are our different partners. When you have a company, you have to work with different partners. So with antibodies, we're working with LifeArc, a branch Medical Research Council, with Aptamers, the Aptamer company. We're also looking at fluorescent oligonucleotides as detection systems. I haven't mentioned this, a company called Nemdex. And the Lateral DX are a lateral flow company, so they can produce the kits, the actual the prototypes, we hope, by Christmas, of the what you'd call rat test. The confirmatory test is with Rosalind Franklin. And this is our so-called IND package. We already have it made to purity that should be expected by a company called Bachem. We have 40 grams of it. So we have lots. If anyone wants to try our MVP, we have it, as you can imagine. We couldn't afford to buy the other 30 grams, but they're sitting on it in Switzerland. So we've still got lots. So to summarize a novel and effective treat for Alzheimer's, what I would suggest is this, that you start off with a pre-symptomatic pair of tests that could be done for everyone or anyone. You then go to the doctor in that pre-symptomatic window, and if your T14 is raised, if that is indeed a diagnosis of Alzheimer's, before you have any symptoms, you then get our drug, and if it performs in humans the same way as it's performed in mice, big assumption, then that means you take that for the rest of your life, but you never then get any symptoms. So that's what we suggest as a package, which would be easy to roll out on the National Health Service. It would be relatively painless. It doesn't involve complicated surgical interventions or painful or distressing things done in the hospital. So it would be a plausible package, and that's what NeuroBio is trying to do. So to conclude, this took ages to do this slide, so I hope you're impressed by it. Okay, so the T14, T30 system lends itself to Alzheimer's disease and to primary testing and lateral flow testing, and that's our companies there, to secondary testing with the Rosalind Franklin Institute, to a therapeutic that then can go through conventionally to the IND, but then has different variants. An animal model, which is much needed in Alzheimer's because the current animal models, like the 5-Fab model, doesn't change tau, for example. There's also applications to cancer, which I can discuss if you wish, which I haven't had time to do, because cancer, again, is an inappropriate form of development. And we've been working with the Olivia Newton-John Centre in Melbourne, as well as a company called Genopat in Spain, and we have some interesting data on that, but I haven't had time to include it. It could be effective there, that's the companies. And then with skin, with Unilever, you might imagine there's lots of people interested in skin and aging. I think if we developed an anti-wrinkle treatment with T14, that would overpass the Alzheimer market, very sadly. Yeah. And then there's the general aging and longevity, and we're now working with the CEDAR Center in California. And then there's also an application for diabetic retinopathy, where again, the degeneration there, it shows in animal model mice, the Akita model mouse is packed with T14 compared to the controls. That's what this hospital in Milan is writing up now. Again, we shared our agents with them. And then finally, the fact that we can detect mood disorders might be of useful in adolescent psychiatry, where the big question is how you evaluate a mood disorder and whether you medicate your patients or not. And I gather this is done entirely by subjective interviews. It's not done at all by any biochemical readout. So we're talking with some consultant psychiatrists about setting up an early trial of swabbing their patients with mood disorders to see if we can differentiate those that need to be medicated from those that don't, according to a biochemical test. So as you can see, the tree has grown a lot from this rather basic idea that chemistries had novel functions. But that's what's exciting about doing science. If you'd like to join in any of these aspects, or if you work with any of these aspects, and you'd like to share and have any of our reagents, I'd be delighted to send them to you. And meanwhile, you're very welcome to this talk and to come back with any questions. It's 40 years of my life summarised in, it's a minute of my life per year, so it's quite a lot. Thank you very much.
Well, that was quite a talk. Thanks, Susan. That was wonderful. We're open for questions, and maybe I could just start with a question. It sounds like a bit of T14 is good for you, but too much is bad for you.
Exactly.
How do you know how much to give then?
Well, that's it, yeah. Well, in Alzheimer's...
Or how much to block?
Yeah, I think in Alzheimer's you would certainly want to block it.
Yes.
Yeah? Because, as you say, there's a balance.
Yes.
That would apply more to issues in the skin, for example. So we know that with psoriasis or eczema, for example, which I would argue is in excess of T14,
right,
that could be treated with local NBP14. Whereas, dare I say it, with aging, if you wanted an anti-aging, little bit of T14. Yeah, so that's an example of the balance. I think in the brain, we can't afford ourselves that luxury, and that if you have excessive T14, as shown in your CSF, or indeed in your nasal, then you would, and that would just be in your brain, it wouldn't be going throughout the body. Yeah. You might get a bit wrinkly, possibly.
And just one more, apolipoprotein E4, how does that work with this whole system?
Okay, well that again, I would argue is a downstream agent, yeah?
Yes.
Because that affects generically cells, yeah? And so why our system is upstream is it's selective to cell groups, but then it will trigger, and I'm sure, we haven't looked at apolipoprotein, but I'm sure that that could, in the pathology, show part of that profile.
Sorry, over here.
Yeah, sorry, so I had a question with one of the earlier slides where the T14 seemed that the T14, I guess like blocking it or as much of it as possible, you proposed would basically prevent you from developing symptoms at all afterwards. I guess at this stage in the research, how certain are you and your team that the T14 is sort of the first step in the reaction?
Okay, well, of course, in life you can't be completely certain, but the fact it seems to reflect so faithfully the Braak staging, even at the presymptomatic stage, and we've looked both in the hippocampus and the nigra and shown that it does correlate very closely with, as sure as amyloid people would be, yeah, when look what they've done. Yeah, so, yeah, I can't be sure, but it does, and the other thing is we have a narrative. We can actually say why we think it would be the case, you know, and I think that helps a lot. So we can't be sure, but the more we do, the more we vindicate it, and the more we work with other groups, and we give them our stuff, and that again sort of fits in. So, of course, I always keep an open mind. I said to Henry, if someone says, you know, this you can't account for, I will wave the white flag and say fine, because that's how you do science, you know. You admit if someone suggests something that isn't right. But for the moment, the story seems to be holding. If someone comes along and shows we're wrong, then of course, yeah, we're wrong. Yeah.
When you, early on, you showed the peptide had homology.
Yeah.
What was the significance of that homology?
Oh, that's how we discovered the T14, actually. We've got rather sniffy about amyloid since then, as you've seen. But the significance was a long time ago, and I was preparing to teach about Alzheimer's, and I was looking at amyloid precursor protein. Given I'd spent a lot of my life working on acetylcholinesterase, showing it had these novel functions and so on, I thought they were comparable to amyloid precursor protein. And given I didn't have a science background, liberated from dogma or actual knowledge, I thought they might be the same molecule. When I suggested this to my colleague, everyone laughed at me. But then they did the sequence homology search and found there was this comparison, which is how we stumbled across, if you like, the T14. So that's the only significance, is it seems to have about a 50% homology.
Yeah, it looked like good.
Yeah, exactly. We got very excited. You know. I feel if there was a biopic one day, you know, my friend saying, "Get over here immediately." And you said, yeah, and that was the advantage, by the way, of the college system, of the fact, you know, you talk at lunch. Because I taught neuroscience and pharmacology, and my colleague, who's on medical, did biochemistry and pathology. So someone called David Vo. So thank you.
Sure.
So it looks like the homology was like close to the cleavage site.
Mm-hmm.
Do you think it's the same secretase as the producing
Sure,
area
yeah.
that produced this T14?
Yeah, well, I think it's rather non-specific. We know trypsin. We looked at the trypsin cleavage. What David has done was look at IDE, insulin degrading enzyme, found that also worked. Yeah. So my own view is that probably in the early stages, if the cell is damaged and the membrane-bound cholinesterase is then naked in the extracellular matrix, it was subject to be non-specific proteolytic degradation. We happen to show it's trypsin, as you can see from our antibody.
So do you reckon that there's a role for T14 in any other neurodegenerative conditions like vascular dementia or frontotemporal?
Certainly, in Parkinson's disease, yes. Frontal temporal lobe dementia, I'm not so sure, because they gave us, the Spanish clinic gave us samples from FTD, and we didn't see the same thing with FTD. And I gather FTD doesn't affect the brainstem very much, it doesn't affect those isodendritic core cells, which actually shows that what we're looking at is related to the isodendritic core. So it's a shame it doesn't affect FTD, but thank you for that. But Parkinson's, yes.
Alice.
Thank you. This looks fantastic. It'll probably take some time, obviously, to get to these stages. And I'm sorry if I missed at the beginning, but what do you think that this says about cholinesterase inhibitors and when we should be using them in patients?
Well, the problem with cholinesterase inhibitors, you have the side effects as well. Galantamine. Well, first of all, they don't bind as well to the allosteric site, and also they are affecting only the cholinergic. They'll affect, they'll preserve acetylcholine, but not other things. So my own view, I gather from actually Mark Yates, who's an ex-student at Henry's, that he's rather wary of cholinergic inhibitors and cholinesterase inhibitors, and he uses Suvanade as his drug of choice, which I see is touted widely on your adverts on TV.
Well, I haven't watched much TV, but my friends have been asking about it. So
Yeah, Suvanade, he uses it. And certainly in the UK now, what's really interesting is the lecanemab, although a rich person can have it, the National Health Service don't think it's effective enough. So, you know, we're in a bit of a mess there. And I don't know if they use Suvanade in the UK. But,
I mean, something like ribostigmine is usually very well tolerated in
Yeah.
the form. And because the evidence is to give it in people who have established dementia.
Mhm.
I just wonder if we should...
Well, certainly it would help. I mean, if you are supplementing the dwindling supplies of acetylcholine, yeah. But bear in mind, I would argue that what's happening in Alzheimer's is you've got the dopamine, the serotonergic and the noradrenergic cell groups all, and I know there's a lot of evidence now for the locus coeruleus and the noradrenergic neurons to be very severely affected. It's not going to do much for them, yeah.
Alice, by the way, is the violinist I was telling you about.
Ah, so you know Mark Yates' wife, Anna?
I do.
Yeah, exactly, yeah.
Any other questions? Good to go.
Yeah, I'm curious about your decision to go from academia
Oh.
a private sector company. And I mean, how do you go about that? You've got a lot of staff, but it's a lot of money.
Oh, tell me about it. Yeah, well, it's a kind of, in life, how things happen. And if I was to give you must always be open to things. So just very quickly, so I was a so-called Don at Oxford, which is a very jammy life, especially I wasn't married at that time. So I lived in college. I had 100% disposable income because you have a free, very nice apartment in the centre of town. As long as you don't mind changing, every evening you have nice dinner and nice lunches. You talk to economists, historians, linguists, have lovely wines, as you can imagine. So what's not to like, yeah? So that was my life. And, looking out the window, having this idea and so on. So if someone had said you're going to start a company, I'd have thought they were nuts, yeah? But then what happened is I had this idea, and Oxford University, and I don't care if this is on record, Oxford University, I don't know about here, were really not very helpful with intellectual property. I don't know if this is chiming with anyone's experiences here, but they were both greedy and incompetent, and that they wanted, to own the intellectual property, and you're nodding, yeah. So luckily, I could be different because I'd worked at the Royal Institution. I'd left under a cloud there, which meant we settled out of court, which meant, unlike many academics, I had sufficient funds. Instead of giving it to a taxman, I paid for one of my own postdocs. That postdoc happened to be the person that did the experiments that got the patent, so I could argue that I'd paid for it myself, not the university. So therefore, I owned the IP. But as you might imagine, I had to leave. So that's when I set up and we're still on good terms, Oxford University, and we collaborate with them and so on. But it wasn't really, it was something I wanted to do anyway, because I was fed up with the endless cycle of grants and the long time that takes and the wasted time writing grants that weren't approved and so on. And the lack, I seem to... yeah, well, yeah. So...
Academic freedom.
Yeah, well, actually, Francis Bacon coined, and I can use my classics roots here, the experience were either lucifera or fructifera. Anyone who speaks Latin, he said, experience were either light-bearing or fruit-bearing, lucifera or fructifera, yeah? And usually in academia, you're on the business of lucifera, shedding light. Business is usually in the business of fructifera, bearing fruit. And for me, this is both, because I'm using my lucifera experiences and, of original research to then apply that to actual products, which is very, very pleasing, to go and play my harp upstairs, to know that I've helped possibly in the treatment of Alzheimer's, You don't have to justify getting up in the morning, doing that.
I think it's super challenging at a university to actually take your finding to something that's commercially viable.
Yeah, well, it's not for the faint-hearted, and you have to learn very quickly because you have all these, as you can imagine, venture capitalists and people, and you have to learn very quickly the jargon and the ways, and I wanted to do that. I didn't want to just say, oh, I'm an academic, I don't know, someone, because that's where